Good evening, friends. My name is Gautam Das. My class is GT chemistry classes, where I teach chemistry mainly for the JEE Mains, Advanced, NEET, and whatever. Anyway, let's discuss about regarding the stability of carbocation. Let's take few examples for stability of carbocation. Now, first of all, regarding stability of carbocation, we have to know one thing, that carbocation is what? Carbocation, if we see some characteristics of carbocation, it's obviously sp2 hybridized, that we know. That means geometry wise is trigonal planar. These are all characteristics. This are everything actually in both syllabus. So bond angle is around 120 degree. It is diamagnetic, we know. Now the main thing is that the central carbon atom, how many electrons are there? Suppose I am taking this R3C plus. Suppose I am taking this. So how many electrons are central? If we consider central carbon atom, central carbon, which is sp2, there are only 6 electrons. That means it's 2 electrons short of octet. So it is electrophilic in nature. That means it is electron deficient, electrophilic in nature. And since we have been discussing the characteristics, one more property or 2 more properties. One property is that it is diamagnetic, we know. We also know the carbanion is also diamagnetic, but free radicals, so they are paramagnetic. Another thing is that they are achiral. Actually, all sp and sp2 carbon, they are achiral. Now these are all actually board level things, characteristics. Now before going into the examples of stability, whenever we are saying carbocation stability, that means something is electron deficient. That means something is electron deficient. So anything which will increase the electron density, any group or atom or anything which will increase the electron density around the central carbon atom will actually increase its stability. Isn't it? If I am very hungry, then I have to feed myself. Okay. So that means whenever we are considering carbocation stability, any electron releasing group attached to it, any electron releasing group, it may be plus M, it may be plus R, it may be hyperconjugation, it may be plus I. They will actually increase the stability of carbocation. Similarly, if any electron withdrawing group, now suppose this group is electron withdrawing. Suppose, let's take another example. Suppose we are taking this like this. Suppose we have taken like this. Now this is electron withdrawing. Suppose this group is electron withdrawing. What is it is doing? It is pulling the bond pair of electron away from this carbon atom, making it more electron deficient. So it is decreasing its stability, isn't it? That means any electron withdrawing group attached to the central carbon of the carbocation, be it minus M, minus R, minus I, will actually result in decrease in the carbocation stability. Hopefully this we all know. Now once we know things, this is the basic thing. Obviously some other factors will also come into play as we go to higher levels, like if it becomes aromatic, quasi-aromatic, then it becomes stable. If there is some examples of Banksian resonance, which is very favorite for JEE Advanced, which is this case of sp5 hybridization, then also their stability increases. Then there are a few things which are exceptions actually, which we have to consider. Anyway, let us start with an example, a very simple one. Let's start with a very simple one. suppose the question is like this. I'm giving you 5 carbocations. OCH3 CH2 plus, number 1, number 2 CH2 CH CH2 plus, which is an allyl carbocation. Then we have CH3 CH2 CH2 plus, then we have CH3 CH CH plus, and then we have Cl CH2 CH2 plus. And you are being asked, this is a very common question, and very simple question rather, of JEE main standard and NEET standard, and you are being asked to arrange them in order of decreasing stability. You have to arrange them in order of decreasing stability. Now let's see what is happening in each of them. Okay, let's see. Actually, it's GOC is all the combination of the basic factors which we have learned. You know. So let's see what's happening. Let's see. First, check is the case of number 1. Now, if you see number 1, which is this methoxy-methyl carbocation. Now here there are 2 effects which are possible. One is plus M effect, another is minus I effect. Carbon and oxygen belong to the same period, so obviously the size and energy gap between the overlapping atomic orbitals is quite less. So in this case, plus M is greater than minus I. That means this. This is quite a stable carbocation, because if you look at this carbocation, here all the carbon atoms, all the atoms, sorry, not necessarily carbon atoms, have completed octet. Now let us see. Let us take number 2, which is an allyl carbocation. Now what is happening here? We all know there will be resonance, delocalization. Now what is happening in 3? Simple case, CH3, CH2, CH2, an alkyl carbocation. This is, there are 2 alpha hydrogen atom, there will be hyperconjugation, as well as there will be plus I effect. Now let us take leave the 4 for the last. Let us take 5 first, which is Cl CH2 CH2 plus. Now here there is a minus I effect group, electron withdrawing group, attached to this carbon atom. So compared to 1, 2, 3, 4, 1, 2, 3, sorry, 5 is obviously will be less stable. Now let us take the 4, number 4. Now number 4 is a vinyl carbocation. Now vinyl carbocation, in vinyl carbocation, I think you already know this thing. This carbon atom is sp hybridized. While in all these cases, the central carbon atom bearing the positive charge are sp2. If we simply take the vinyl, let's check the diagram. Why should you take my word that it is vinyl sp hybridized? If we simplest vinyl carbocation, if we look at its diagram, actually the bonding, there is this pi bond. Now this is the vacant 2p orbital. Now this carbon atom is sp, 2 sigma bonds around it. This is the pi bond, this is the vacant 2p orbital. Suppose I am considering this to be x-axis. This sigma bond and this sigma bond is along x-axis, and this is suppose along y-axis. The pi bond is suppose along y-axis. Okay, like this. So now this vacant 2p orbital, p, this p, if suppose I have considered this is the overlap of 2py, then the vacant 2p orbital will be 2pz, which will be at the positive charge. That means this is the x-axis sigma bond, this is the pi overlap, and now something like this, which is perpendicular to this pi overlap. What does it actually mean? It means that this pi bond cannot stabilize this positive charge. There cannot be resonance. There cannot be resonance at all, isn't it? Here, if you consider in this case, now you may say why the resonance is occurring here. For this, if you look at the structure, of allyl carbocation, this is the positive charge, and this is the pi bond. So this pi bond is simply overlapping with this, and there is simple resonance, but here resonance stabilization not possible. Now, so up till 1, 2, 3, there is always stabilizing effect. Then 5 is getting destabilized to some extent, but still it is sp2 hybridized. But here, this carbon atom is becoming sp hybridized. Now we all know, this is the bonding part which you have done in class 11, that hybridization of any atom, so in this case carbon, with increase in s cation hybridization, the electronegativity of that atom increases. That means sp hybridized carbon is more electronegative than sp2. Once we know that, so that means what? More electronegative carbon cannot accommodate positive charge to a greater extent. So that means this, only in this case, in number 4, that is the vinyl carbocation, the carbon is sp hybridized, isn't it? And all in other cases, the carbon, the positive charge is on sp2 hybridized carbon. So we can simply say the 4 will be least stable. We are now doing the stability order. 4 will be least stable. Now among them, really, if we consider the effects, we know this is very, very important. Plus m is greater than plus r, greater than hyperconjugation, greater than plus I. Very, very important. Student more this confused here. Why plus m is greater than resonance? You may say that in both the cases resonance is occurring. So why plus m is greater than resonance? If you look at this structure where plus m is occurring, here all the atoms have completed octet. But this is not the case here. This has not completed octet here. Resonance is occurring. Two equivalent resonance structure is there, but not complete octet. So plus m, where plus m is occurring? In number 1. So number 1 will be most stable. Then number 2, plus r. Then hyperconjugation inductive effect. Number 3. Now 5, although it contains electron withdrawing chlorine atom, quite highly electron withdrawing, which will exhibit minus I effect. But after all, this carbon atom is sp2 hybridized, which will be less electronegative than sp hybridized carbon, so it can accommodate the positive charge to a greater extent than this one. So even 5 will be greater than 4. So our stability order will be this. Hopefully we have understood this thing. Now let us consider another question. Now actually these are the questions obviously, but if you want to obviously for this type of questions you can subscribe. I hope you subscribe my channel, and if you like the video, press the like button. But actually it will be better for you if you join my classes. Anyway, I take both online and offline classes. Before going to the lessons, I'm just giving you another thing. The details will be given below, but I'm just mentioning you one time that you can contact me in this WhatsApp number. You can leave a message there if you want to join my online or offline classes for only chemistry. Anyway, let's continue with our carbocation stability. Let's take another case, another very common question which comes JEE mains or NEET level. JEE advanced will go a little later on, maybe in the next video, not this video. Let's take another question. let's keep this 5. Simple benzyl carbocation. This is para-methoxybenzyl. This is para-chlorobenzyl. This is para-nitrobenzyl carbocation, and this is para-methyl benzene carbocation. Again, you have to arrange them in order of decreasing stability. That will be most stable first and least stable last. Now, in this type of question, you can obviously cancel out one thing, which is, this is a relative question, which is common in all of them. Now, in all of them, the Placer effect of the benzene ring is occurring. Placer effect is benzene ring is occurring in all of them. Okay. Now, we already understood one thing. We have gone through this one thing, that any electron releasing group will increase the stability. Any electron withdrawing group will decrease the stability. I mean, if there is no such group present, then it will remain as such in between in those two. Now, if you consider this one, number 2, OMe, here plus M is greater than minus I. I've already said in the last question why plus M will be greater than minus I. But if you look at this, how plus M is actually operating. This is the carbocation. Obviously, for resonance planetary is important condition, and all the p orbitals will be in the same plane. So this is going to this, and this is comparating octet. This is Placer effect. So now here chlorine, again for chlorine minus I as well as in this case plus M can occur, but here minus I is greater than plus M. Now you may ask why in this case plus M is greater than, why minus I is greater than plus M. After all, minus I is just pulling or pushing tendency over a covalent bond. M is actually giving or taking off electrons. So, but here just remember one thing: whenever M or R, when you are considering M's particularly, then actually you are considering the overlap of atomic orbitals involved. So whenever there is this big size and energy gap between the overlapping atomic orbitals, the overlap becomes less effective. Now, so that's why whenever we are talking about atoms belonging to the same period, they do not differ in much. They don't differ much in size. Those atomic orbitals involved do not differ in differ much in size. Like here it is carbon, oxygen. But here, whenever we are considering atoms belonging to the different period, to be very precise, just you can take it as like this. Okay, just consider like this. Whenever we are considering atoms belonging to the same period, then mesomeric effect will be predominating over inductive effect, and when they are contradictory to one another, and whenever they are in different period, since we are considering organic compounds and different to carbon, suppose, then the inductive effect will be predominant over mesomeric effect. There will be mesomeric effect, but inductive will be the resultant one. So overall, it is electron withdrawing. Now, nitro group, we all know, will exhibit minus I and very strong minus M. Now, methyl will exhibit hyperconjugation as well as plus I. Hyperconjugation is more important than plus I. Now, if you look at this, how hyperconjugation is operating. You all know hyperconjugation is no bond resonance, and all those are board level things. This CH bond is breaking, creating a double bond. As soon as a double bond is formed, 1, 2, 3, 4, then this and this pi bond will come here, and this is coming here, and so this is the hyperconjugation. So this 3 alpha hydrogen can go into the mode of plus I effect. Now let us consider, remembering the very fact, electron releasing group will increase the stability, electron withdrawing group will decrease the stability. There are 2 such compounds, 2 and 5, where there are electron releasing group. Now we already know the order: plus M, plus R, hyperconjugation, inductive effect. So obviously 2, stability order, 2 will be most stable, followed by 5. Now, before going into 3 and 5, we have 1. Now, phenyl is common to each and every. So we are considering Placer effect exhibitor phenyl because it is happening in every case. Because there is no SIR effect here, static inhibition or resonance effect here. Moreover, it won't occur in these cases. It mainly occurs in cases of carboxylic acid, orthosubstituted benzoic acid, or orthosubstituted anilines, and N anilines or whatever. Not in these cases. So here, before going to electron withdrawing group, we have this thing where there is no electron withdrawing group or electron releasing group present. So it will be number 1. Now, chlorine and nitro, both are electron withdrawing, but we simply know that minus I effect of nitro is much greater than that minus I effect of chlorine. Minus I effect. Also, my nitro exhibits minus M to some extent. So this will be least stable than this. So the stability order is simply this. Okay. Now, now let us take another one. Since we have involved benzene ring, let us take another one. Another question. This is also pretty simple. I'm just changing the position of those groups. I hope here in the original question it was earlier question it was OMe. It is chlorine. It is nitro, and it is methyl. 2, 3, 4, 5. Now, again another important concept. This is actually board level concept which we have already done in, I think, in class 11 level. Most of the students are. Whenever two groups are meta with respect to one another, they don't enter into resonance. That means they are not involved in conjugation. Mesomerism won't occur whenever those two groups are meta to one another. That means, suppose this is a carbocation. So if a group which can exhibit actually meta effect normally, when at ortho and para cannot exhibit can exhibit plus M effect when at ortho and cannot exhibit plus M effect here. It won't enter into here because it will end somewhere here or here and something like that. Electron releasing property. So basically, you don't have to remember all those big things. You just have to remember whenever two groups benzene ring either attached to one another, that maybe plus M minus M groups are two groups attached with respect to meta to one another, then the mesomeric effect won't come into play, or the resonance effect of the groups will not come into play. Only inductive effect will come into play. So here we know. Now here OMe minus I. We have already said one thing, that OMe can exhibit plus M as well as minus I. Now here plus M is not possible, so only minus I. Chlorine only minus I, here only minus I. And here hyperconjugation is not possible. Here hyperconjugation is not possible. Not possible. Only plus I. Here minus R or minus M, here minus M is not possible. So all are these 2, 3, 4 are electron withdrawing, and this is the only group which contains an electron releasing group other than phenyl, which is common to everyone. So stability order, we can simply say here the stability order 5 will be most stable, then come 1 without any electron withdrawing group. Then again minus I effect decreases, and we know that minus I effect, if we take the general one, NF3 plus greater than NR3 plus greater than NH3 plus greater than SR2 plus greater than nitro greater than CN, then SO3H, then CHO, then COR ketone, then come the acid, then come acid derivative, then come the halogen, fluorine, chlorine, bromine, iodine, then come OH, OR, NH2, and so and so. So my minus I effect decreases from nitro to chlorine to OMe. So this is exhibiting maximum minus I effect, making this least stable or most unstable of the three lot, and this is least minus I effect, making it relatively more stable among three. So it will be 5, 1, 2, 3, 4. Hopefully you have understood one thing. Now let's take another question. Because every day I cannot upload actually videos because of my classes. I remain quite busy. My offline classes are in Kolkata, obviously. Those who are outside Kolkata, they can only go for my online classes and so and so. So today I've got some time, thankfully. So that's why I'm uploading some questions. This is a basic question I've seen the students are actually missing. Now let us consider another question. This is a very simple question, very simple one. Suppose I have taken CD3. I think most of you know this already. carbocation and CH3 plus carbocation, and just I then tell them which one is more stable. Now this is pretty easy. I think you can do. Just pause the video and try on your own. I think you can do it. Now here two things are happening: hyperconjugation as well as plus I effect. Both are electron releasing, but we already know, actually, according to Baker-Nathan effect, hyperconjugation predominates over inductive effect. Over inductive effect. Now, for inductive effect, plus I effect, for plus I effect, deuterium is preferred over hydrogen. That we all know, class level. But for hyperconjugative effect, CH bond is preferred over CD bond. Very simple. What is happening in hyperconjugation? We are breaking a CH bond and it is going into resonance. We are breaking a CH bond, isn't it? sp hydrogen carbon, they're breaking the sigma bond and it's getting into resonance. You all know that thing. Like suppose we have already seen one thing. This sigma bond is breaking, and we are getting this. This is the hyperconjugation, no bond between this, so that's why it's called no bond resonance. These are all basic level things. Anyway, now, so CH is preferred over CD. Why? Because CH bond energy, whenever we are considering bond energy, CH bond energy is less than CD. So obviously it will take less energy to break CH, easier to break CH bond can be break easily. So obviously that's why this thing. Now here we already know, this is the very, very common mistake the student make. Hyperconjugation predominates over inductive effect, and whenever we got hyperconjugate, CH bond is more preferred over CH3. So here there are 9 alpha hydrogen and 9 deuterium atom. Hyperconjugation is predominating over thing, and so we can simply say 2 is more stable than 1. Stability order. That means following this thing you can simply say just a moment. Following this thing, you can simply say why this is happening. I think that this has come in 1 year question recently. Now you can say that why this is more stable. This is stability order. Now, if I consider this 2 alpha hydrogen atom, there are 4 alpha hydrogen atom in either of the cases. So we are not considering, this is a relative question. We are not considering this 4 alpha hydrogen atom. We are considering this alpha hydrogen atom, this alpha carbon atom. So here there are this hyperconjugation occurring, and there is hyperconjugation occurring, which is CD, which is much to a less effect than compared to this. So this is more stable than that. Having said that, now already but if we consider this one, if we consider this one, now here there is no hyperconjugation. There is no chance of hyperconjugation because there is no alpha carbon. So no question of alpha hydrogen atom. So here there is only plus I effect, and we already know plus I effect is D is greater than H. So obviously here the plus I effect is more than the plus I. It's hydrogen does not exhibit actually either plus I or minus I. It's inductive effect. The basic is it's inductive effect of hydrogen is technically 0. So here this will be actually more stable. We will continue with a little more tougher questions in the next carbocation stability video. Please subscribe the video, and if you want to join my classes, see the note below this. You will get the number. Okay, thank you.